pleasure to have Dan Cristofaro-Gardiner here. Really low-dimensional topology and dynamics has changed dramatically in the last couple of years, and his work has been sort of key in this. So go for it.
Okay, well, thanks very much for the invitation. It's a great pleasure to be able to talk about this here. So let me say the plan actually for both of the talks. As Paul was saying, it seems like in the last few years, there's really been a lot of progress in our understanding of low-dimensional symplectic dynamics. You can look at some of the classic papers from the 80s, the 90s, 2000s, and just in the last couple of years, it seems like we're finally answering almost all the questions that were brought up there. So I want to tell you a little bit about how this works, but I'm going to do a kind of example-driven approach. So I'm just going to tell you about 2 examples in depth, maybe do a little bit of more surveying. But so just then, like a major disclaimer is that I will not, I make no claims to cover all important advances in this area. Just want to give you a flavor for it. Okay. And also, this is a very biased selection of examples. These are just 2 examples that I like a lot. Okay, so yeah, I really want to make this concrete. That's another point in picking the problems is I really wanted to pick concrete problems. Also, while I'm making ruminations, Lisa was saying during her talk, she really likes questions, and I feel the same. I want you to ask lots of questions. In particular, in this first lecture, I really tried to keep things as kind of unsymplectic as possible. So you're really meant to understand it. So stop me if you don't. One more announcement is that if you go to my website, which just is my name, you can actually find the slides. So if I skip a slide and you want to go back, just go to my website and look under slides, and you can actually find these slides. Stop me if you can't find them. Okay, so I want to make things concrete, and so here's a group. This is the group of volume-preserving homeomorphisms of the n-dimensional disk. So you just take the standard disk, and they're compactly supported in the sense that they're the identity near the boundary. So, but importantly for the talk, we're talking about homeomorphisms. So I just imagine for every open set, I look at where it goes, and I want the volume of that open set to be the same as the volume of where it goes under this homeomorphism. So this is called the group of compactly supported volume-preserving homeomorphisms. And a theorem of Fati from the 70s is that this is a simple group if the dimension is at least 3. A natural question then that Fati asked in the same work is, what happens in the 2-dimensional case? Just a comment, you might also wonder, why are we studying the compactly supported homeomorphisms? Why not just study all of them? Well, if you're interested in these simplicity questions, the compactly supported ones are just a normal subgroup of the full group. So it's not interesting to study the simplicity question for the full group. Well, I just mean simple in the sense of groups. So you'll see actually that's a good question when I state our results. So I just want to know, does it have non-trivial proper normal subgroups? That's right. Okay. Any more questions about the rules of the game or anything? Okay. By the way, also just some motivation. You might wonder, why are we doing this? Well, there is a general philosophy, I guess, going all the way back to Klein, relating the algebra of groups like this to the underlying geometry. So you might hope that the algebra of this group is saying something interesting about the geometry of area-preserving maps. So 2-dimensional case had been a mystery. Let me give you more context by talking about how it works for some other cases. So the questions really go back to Ulam, who asked, okay, what if I just look at homeomorphisms, not preserving any kind of geometric structure of the n-sphere? Is that a simple group? That's a question in the Scottish book. And in the 30s through 60s, the work of various authors told us that, in fact, it's simple for any connected manifold. So then Smale asked in the 60s, how about diffeomorphisms? And in the 70s, we got a sense that that group's simple. Okay, it gets interesting when we put more geometric structure. So I can look at, for example, say volume-preserving diffeomorphisms. It's the case that was studied by Thurston. So, so I have a group. I want to know if it's simple. presumably the first thing to look for are homomorphisms. So Thurston says that there is a homomorphism out of the group of volume-preserving diffeomorphisms. I won't define it for you for time reasons, but there's this flux homomorphism. So it's not in general going to be simple. But on the other hand, Thurston shows that its kernel is simple. Some of the other ones I'll go through a little fast. In the symplectic case, you still have flux. If the manifold is closed, then Banyaga showed that the kernel of flux is simple. If it's not closed, there's a kind of secondary flux called the Calabi homomorphism. And then the kernel of the Calabi homomorphism is simple. Okay, so this gets us now to Fatty's work, and hopefully you get a better sense of the motivation for the question. So Fatty was thinking about the case of volume-preserving homeomorphisms. So if the dimension is at least 3, he shows there's a similar picture. It's a mass flow homomorphism. It's quite similar to flux. It has a simple kernel. But the n equals 2 case, Fatty doesn't know. And so that's, of course, the motivation for why we're interested in this case of the disk. And maybe at the end of the first lecture, I'll give a story for a general surface. But the case of the disk is concrete and contains most of the interesting stuff anyways. Well, it's just a quotient of appropriate homology group of a manifold.
It's not simple to describe. It's not like.
It's pretty simple to describe. It's a quotient by a discrete group of just one of the cohomology groups of the manifold. So it is pretty simple to describe. Yeah. Any more questions while I'm stopped? Okay, so there's a general picture that I want you to get from this. So for all these cases, so either the group is simple or you get some kind of natural homomorphism. Kind of gets to Mark's question. I mean, I guess I didn't tell you anything about how you construct this flux, but it's geometrically constructed and eventually usually get to a simple kernel. Okay.
So it's an abelian group.
It's an abelian group. Yeah, that's right. That's right. Yeah, but the case of area-preserving homeomorphisms had really been quite a mystery. And right, so our theorem is that in the two-dimensional case it's actually not simple. And it's actually a little bit stranger than that, because we show that it's not simple, but we don't do it by constructing some kind of natural homomorphism out of it. We don't construct like a flux or something. Also, and this final point is a bit vague. It doesn't seem to fail to be simple, at least with our current knowledge of it. It doesn't seem to fail to be simple for one particular reason. So it's not like, here's the normal subgroup, that one's simple. There's lots of normal subgroups. There's this quote by Leroux. It says it's actually radically different from the case of diffeomorphism groups. Also getting to Mark's question, there is a natural topology on this group. You could look at the C0 topology on the group, and our subgroups are not closed in the C0 topology. They're just normal subgroups, whereas the other ones tend to be closed in their natural topologies. So some pretty strange thing. Okay, so, and it's proved using these kind of low-dimensional symplectic methods, which of course were not really known to Fatty. So that's kind of why Fatty was unable to do this. And in fact, we'll even see that, for example, like the Seiberg-Witten invariants play a role in the proof. So, okay, so are there any questions? I tried to say not a huge amount so that there would be lots of time for questions. Yeah, great question. So the reason that Fatty's argument breaks down and the sort of flavor of it is that Fatty uses a fragmentation property for homeomorphisms. So there's a notion in these papers that is very important called fragmentation, where what fragmentation is about is I can imagine taking one of these homeomorphisms and trying to cover the disk by smaller disks and writing the homeomorphism as the product of homeomorphisms that are supported on these smaller disks. And Fatty's argument critically uses this fragmentation. And in fact, Leroux had shown that that's exactly the thing that the simplicity conjecture depends on, whether or not fragmentation in a very strong sense hold. So in order to get Fatih's argument to work, you need a quite strong fragmentation property for homomorphisms that he's not able to prove. And the reason he's not able to prove it is because it's false. So LaRue shows that the simplicity of this group is equivalent to whether this strong form of fragmentation holds. Well, it's a kind of a subtle thing. I mean, when Fatih's doing this fragmentation, he just remarks that, the thing that he does doesn't work for dimension 2, but he's not able to prove that it cannot be made to work. I mean, his argument uses that the dimension is at least 3. Okay. Are there more questions?
You can ask questions even if you're not sitting in the first row.
Right. I do agree. And like I said, I tried to give kind of fewer slides so that people would ask a lot of questions, kind of cover the main points. Yeah?
What is the structure of homeos C d squared omega?
What is the structure of it? Yeah, so I mean, I guess it's a question of... Well, I'm not sure I completely understood the question, but I think it's leading to something that I say on later slides, which is, okay, we show that it's not simple, but that doesn't tell you, what it is, or it doesn't, you could still ask what's the normal subgroup structure. So, for example, we find a normal subgroup, I'll tell you what the normal subgroup is, but later we showed that that's not simple. And then it's actually kind of a funny story because, okay, we said that that one's not simple because there's this other normal subgroup, but then we showed that that one's not simple. And so this kind of chain of things being not simple has yet to converge to anything resembling a kind of clear understanding of the normal subgroup structure. Of course, there are other questions you could ask too. For example, another thing we thought about is the commutator length. You can ask, for the commutator subgroup, you can say, how many elements does it take to write something as a product of commutators? That's also an interesting question, and some people call that something like the kind of algebraic genus of the group. And we showed that the commutator sublength is actually unbounded. So there are kind of other things that one can ask. Yeah.
Do you know whether or not there's a finite dimensional, a finite quotient group?
Also a great question. Yeah. So there's some general arguments, maybe going back even past Fatih, which one can use to show that every normal subgroup of this group contains the commutator subgroup. So all the quotients by any normal subgroup, in particular by the ones we produce, are abelian. But we don't know a huge amount about them. For example, we don't know whether they're torsion-free, whether they're divisible. Would be nice to know. Yeah. Okay. So maybe that's great. Thanks for all the questions, including people not from the front row. Okay, so now, yeah, like I said, I want to just kind of sketch the proof. So I promised that the lecture would be accessible. So basically, I've taken all the non-accessible parts and put it in 2 sentences, and then from the rest, you can learn the proof. Okay. So you should actually understand this, except for 2 sentences, which I will tell you which those 2 sentences are. Okay. So as I said, the proof uses symplectic geometry, but I don't want to assume you know much symplectic geometry. But I do want to point you towards Hamilton's ODEs. So this is a very important system of equations. They're the equations of classical mechanics. So in my notation, the xi are position, the yi I can think of momentum. So I can think of some system. People like to think of maybe the solar system. And this function h is the Hamiltonian, so-called energy function. And I'm allowing my Hamiltonian to depend on time. Okay, so this is a kind of much studied, very important system of ordinary differential equations. And it's useful to encode it as the flow of a vector field, possibly a vector field depending on time. But anyways, this notation phi th is going to come up again and again. So, I'm just doing everything on R2n here. So I have some Hamiltonian, possibly depending on time. I look at its time t flow of this vector field. I get this function phi th. Okay? Maybe we just do an example. So, for example, my Hamiltonian, I could just take n equals 1. So I'm looking at R2. I have this Hamiltonian. People call this the harmonic oscillator. So you can write out Hamilton's ODEs. You just plug in. That's what you get. And so you're interested what happens for different initial conditions? Well, you can just check that the solutions are all going to be periodic. Okay? So any questions about these preliminaries? So this will play a role in the proof. Okay, so let's give this some juice. Okay, so actually, we can use this point of view to show that the diffeomorphism group is not simple. Okay, so just to remind you what we're doing, we're trying to show that the homeomorphism group is not simple. In other words, the group of area-preserving homeomorphisms. But the diffeomorphisms, the ones that are smooth, was known that it's not simple. I mean, I even said that this is due to, say, Badyaga, or maybe in this case, even due to Thurston. Anyways. Maybe even due to Calabi, I guess. But anyway, so let's explain how to prove this using this Hamiltonian formulation. Okay, so I'm going to find a homomorphism, this so-called Calabi invariant, and here's how I define it. So I just explained that if I have a Hamiltonian, I can look at its time t flow, and I get some map. I guess I didn't say, but it's actually going to be area preserving. That's maybe called Liouville's theorem. And at least in the case of the disk, and in some other cases, I can reverse this. In other words, if I have any area-preserving diffeomorphism of the disk, I can find some Hamiltonian whose time one flow generates it. Maybe I have to allow my Hamiltonian to depend on time. And since the map is compactly supported, remember that means it's the identity near the boundary, I can demand that the Hamiltonian itself actually vanishes near the boundary of the disk. Okay, and so here's my homomorphism. Well, I just integrate this Hamiltonian, and I get a map to R. And you can check that this doesn't depend on the choice of Hamiltonian. Okay, I mean, that's a kind of cool fact about life. And that's the Calabi homomorphism. You could imagine that, I mean, it certainly will be the case that I could have multiple Hamiltonians whose time one flow gives phi, but their integral doesn't depend on the choice of Hamiltonian. Let me just give you a picture. Okay, because this was a kind of slick definition, but you'd like to know, like, what does this actually mean, this Calabi homomorphism? Well, I put a beautiful picture by Gies. So you really want to think of it as measuring the average rotation of the map. So how might I define the average rotation of the map? Well, I can take an isotopy from the map to the identity, say given by the Hamiltonian itself. And what I can do is I can look at any 2 points on the disk, and I can look at how they rotate around each other as I let time run from 0 to 1. And then it turns out that I can attempt to integrate that over the choice of all possible pairs of points, and I get a well-defined thing. And that's also the Calabi invariant. So it's measuring the average rotation of this area-preserving map of the disk. So the variation. So I'm saying I look at the variation in the argument as t goes from 0 to 1 of the difference vector between these 2 points. So I imagine picking 2 points, x and y, in the disk. I let t run from 0 to 1. I look at how much they rotate around each other. In other words, I look at the variation in the argument of this thing. And then there's a reasonable way to make sense of integrating this over the whole disk across itself. Okay, so maybe I should pause and see if there are any questions. I mean, up to this point then, we've shown that the diffeomorphism group is not simple. And then remember, I actually said that by work of Banyaga, the kernel of Calabi actually is simple. In this case. Yeah.
Can you just go back to the previous slide and show your other definition?
Sure.
So semantic determinants, looks like the Hamiltonian is valued on S1 across T2, but you had a flow on D2 only.
Yeah, right, good question. Right, so I'm thinking of the Hamiltonian as depending on time, and so I'm just saying I can actually arrange it so that it's one periodic in time, and that's my S1. And that's sort of nice for what's coming.
And you think of that S1 also as the direction vector in the next slide, or is that a different sort of S1?
I think it's sort of a different sort of S1. This is just, the time, the Hamiltonian itself is depending on time. I mean, there is time on the next slide too. That if I look at 2 points, I'm looking how much they rotate around each other as I run from 0 to 1. But I'm just saying I can assume that my Hamiltonian is 1 periodic in time, and that's sort of useful for what's coming. But it's not really like an essential point of what I've said so far. Yeah?
And you don't even need the Hamiltonian. You can do it for any isotopy.
That's right. Yeah, the Hamiltonian just presents this explicitly as an isotopy, but I could have just taken any isotopy to the identity through area preserving.
Do you need the isotopy to be compactly supported?
I think it's good to be compactly supported. Yeah. I mean, I don't know. Probably you can probably do something somewhat similar, but in general, if it's kind of doing something interesting near the boundary, you actually want to sort of take account of that in the sort of theory.
Yeah, I guess if you have an isotopy which does a full twist around the boundary or something, maybe that adds a back term.
Yeah. Right. In this case, it's just nice to have everything be nice and compactly supported. Right. Were there more questions? Yeah.
What's the blue and the green indicate in the picture?
It's Jesus' picture. I think Jesus is just imagining like fluid running around. He's kind of imagining you're stirring a whirlpool. I mean, Jesus kind of popularized this question to some degree. He has this beautiful ICM talk, Knots and Dynamics, where he talks about this, and I encourage you to look at it. And anyways, in the ICM talk, he's explicitly saying, one might imagine in fluid flows that these homeomorphisms actually, do come up, by some kind of singularities developing in a certain amount of time. So I think he's kind of drawing some kind of fluid flow. Yeah. Okay. Any more questions? Okay, so I think we've mastered the diffeomorphism case. Okay, so how about the homeomorphism case? Well, maybe we should go based on Mark's question. So there is a topology here, and we probably want to use it. So the diffeomorphism group, it's sitting densely in the homeomorphism group in the C0 topology. So if we wanted to show that the homeomorphism group is not simple, an obvious thing to try to do is to extend this Calabi homomorphism. And, well, I mean, it's not going to work. I'll explain why it's not going to work, but it's going to motivate some of what's coming. Okay, so why isn't it going to work? Well, the problem is that the Calabi homomorphism is not, in general, continuous in the C0 topology. Why isn't the Calabi homomorphism continuous in the C0 topology? Well, so let's go through the example. It's not hard to come up with examples. So I can take Hamiltonians that are supported on smaller and smaller disks, but that are integrating to 1. Okay, so then by definition of the Calabi invariant is going to be 1. But on the other hand, if I look in the C0 topology, the time 1 flow is converging to the identity. Okay, so maybe we should just remind you of the C0 topology. Things are far apart in the C0 topology if they map points to points that are far apart. Here, if I have 2 points, if I have any 2 points that are not at the origin, as n gets large, they're not moving at all. So, this is C0 converging to the identity. But on the other hand, the Calabi invariant of the identity is 0. So it's not C0 continuous. Okay. So, as I said, just stop me if you have any questions about this. So what can we do? Well, like I said, we're going to actually write down a normal subgroup. It turns out that there's a beautiful bi-invariant metric on this group discovered by Hofer. And you can do this not just for the disk, but really for any symplectic manifold. And I should say a bit about how it works. Okay, so first of all, so this metric, it's called Hofer's metric. To a Hamiltonian, I study the so-called 1 infinity norm, where I look at the difference between the maximum and the minimum of the Hamiltonian. I can call that the oscillation in the Hamiltonian as a function of time, and then I just integrate that as my time goes from 0 to 1. Okay, so now if I actually have a compactly supported diffeomorphism, and I can, well, it doesn't really matter, but I'm demanding that my Hamiltonians are 0 near the boundary. Okay. So if I have a compactly supported diffeomorphism, I can look at the most efficient way to present it as a Hamiltonian flow with respect to this one infinity norm. And that gives me a norm called the Hofer norm. And finally, if I have two diffeomorphisms, I can define their Hofer distance just be the norm of one times the inverse of the other. Okay, so I'll see if you have any questions about the definition. Let me say that this is actually very cool because it's bi-invariant and non-degenerate. So I put an exclamation point here because to put this in some context, if you were dealing with a finite dimensional Lie group, it would be very hard to find bi-invariant non-degenerate metrics like this. So this is kind of critically using the infinite dimensional nature of the group of Hamiltonian diffeomorphisms. So it's maybe at first glance surprising that such a thing even exists. Okay, so I'll stop and see if you have any questions. I just want to say that, okay, so what we're trying to write down a normal subgroup, and remember earlier I was saying that there's a general philosophy that the algebra should reflect the geometry, and this Hofer geometry, the geometry of this metric on the group of diffeomorphisms is going to inspire how we write down the group. Okay, I don't see any questions.
Yeah, I have a question.
Oh, okay.
Why are the diffeomorphisms C0 dense?
Yeah, I mean, that's not so easy to prove, but it's a known fact. I guess maybe it goes back to maybe Lauderock or something like this. But that is very important also for all this is the fact that the homeomorphisms are C0 dense. Okay, so at this point you should be thinking, we have this diffeomorphism group. It has a metric on it. It's even bi-invariant. We want to use it to define a normal subgroup. Okay, so our normal subgroup is going to be the so-called finite Hofer energy homeomorphisms. So I'll walk you through this a little bit slowly. So what's a finite Hofer energy homeomorphism? Well, it's a homeomorphism, and then just as Paul was saying, the diffeomorphisms are C0 dense. So if I have a homeomorphism, I can always approximate it by diffeomorphisms. And what I'm interested in when I do this approximation procedure, does the Hofer distance blow up? Okay, so if I'm finite Hofer energy, it means that I can be approximated by diffeomorphisms in C0 without the Hofer distance blowing up. So if you like, actually, the group of finite Hofer energy homeomorphisms itself carries a kind of metric like Hofer's metric, where I can look at the kind of infimum over all the ways to approximate it. So if you like, you could think of this as the largest normal subgroup on which Hofer's metric could credibly be defined. Okay? And so the reason that it's nice to think about it this way is that it's actually pretty clear that this is a normal subgroup. I said it as an exercise, partly because I don't want to spend the time. But I do want to say that the bi-invariance of Hofer's metric is quite useful for this. I mean, I just explained that the metric is bi-invariant, so hopefully it's not surprising to you that I can construct a normal subgroup this way. Okay, so again, I'll pause, but just to give you a slogan to keep in mind, so think of this as the largest normal subgroup on which Hofer's metric is credibly defined.
But bi-invariance meant with respect to homeo or diffeo?
Just with respect to the group. I mean, so I'm looking at the group of diffeomorphisms. The group here, diffeo, yeah. That's right. But in a way, your question is like exactly getting at the solution to the simplicity conjecture. There are two groups, but the problem is that Hofer's metric doesn't necessarily even make sense on the homeomorphism group. If you look at the definition, I need to write things as a time one flow. So there's only one group at the moment, diffeo, for which I actually have Hofer's metric. And F homeo is the sort of largest subgroup of homeo for which I could credibly even define Hofer's metric. And that's going to be my normal subgroup.
Just a little surprising, but you have but the normality is inside homeo, but the bi-invariance is with respect to
That's true. I agree. But
it's an exercise.
That's why it's an exercise, exactly. You can do the exercise. That's right. I promise that we did not mess up this point in our paper. Okay, so what remains to be done? I mean, are we done? I mean, I wrote down a normal subgroup. It's obviously not just the identity, because it contains the entire diffeomorphism group. So we just have to show that it's not everything. So all I have to do, in other words, is find a homeomorphism which is infinitely far from the identity in Hofer's metric. Okay? So now I'm going to give you a homeomorphism which is infinitely far from the identity in Hofer's metric. So first I have to motivate how to do it. Okay, so if you just remember the definition of the one infinity norm and the Calabi invariant, which you probably don't, that's why I was saying you could go to my website and look at the slides. You'll see that the Calabi invariant bounds the one infinity norm from below. So if I want something that the one infinity norm is blowing up, I might as well try to get something so that the Calabi invariant is blowing up. So I want to try to find a homeomorphism with, let's say, infinite Calabi invariant, where this needs to be made precise. But like I said, everything I'm going to say in this talk, save for 2 sentences, is quite rigorous. So I will make this all very rigorous. Okay, so here it is. Okay, so it's the so-called infinite twist. It was actually proposed not even by us, but by, I guess, O and maybe Fati himself. I actually don't know the whole history. But okay, so it's a twist map of this disk. Remember, this is just supposed to be an area-preserving homeomorphism of the disk. Okay, so what it does is it preserves the radius, and it just twists each circle by an amount depending only on the radius. And the point is that's what that function f is doing. The point is that function is blowing up as r tends to 0. So I have my circles, I twist more and more and more and more. And then I have to say where the origin goes, I just map the origin to itself. And then I need that this should have infinite Calabi invariant. Well, it turns out that the condition that we want is that this particular integral diverges. But that's not a weird condition. I mean, the way you come up with that condition is you first imagine I took a smooth twist like this that was smooth all the way on the whole disk. I compute its Calabi invariant, and it's exactly given by that integral. You just demand that integral diverges. Okay? So any questions about this? So this is the map, and we just have to show that this is not a finite Hofer energy homeomorphism. Okay. So how are we actually going to do this? Well, here's where the kind of Seiberg-Witten type stuff comes in. So what we want to do is we're going to define for every diffeomorphism a sequence of real numbers called PFH spectral invariants. They're going to have the following properties. First of all, they're going to be continuous in the C0 topology. You should contrast that in your head with the Calabi homomorphism, which remember is not continuous in the C0 topology. So they're going to be C0 continuous, and they're going to extend to the homeomorphisms. They're going to recover the Calabi homomorphism via this so-called while law. Namely, okay, so there's just some limit, and for diffeomorphisms, it's supposed to recover the Calabi invariant. And they're going to satisfy what we call the Hofer-Lipschitz property. So the Hofer-Lipschitz property says that if I'm looking at the difference between any two of these spectral invariants, then they're Lipschitz with respect to the one infinity. They have this Lipschitz bound with respect to the one infinity norm on H and K. Okay, so those are the sort of big properties. And remember, I said that that there'll be a part of the talk where I've squeezed a lot of the math. We're getting to that part of the talk where I've squeezed a lot of the work. But so just believe me for the moment that I do have such invariants. Are there any questions about the properties? I guess just philosophically what you should imagine is that, okay, these PFH spectral invariants are going to be defined using Floor theory, where the punch is that they're going to be C0 continuous, so they actually sort of don't have this problem the Calabi homomorphism has. But on the other hand, by the so-called Weil law, they're still strong enough to detect the Calabi invariant. So that's the kind of punch. Are there any questions about that? Oh, yeah.
Why do you call this a Weil law?
Yeah, that's a good question. So Weil's original law was about counting eigenvalues of the Laplace operator on some domain, for example, the disk, and then you can recover the area or the volume of the domain by looking at the growth rate of the number of eigenvalues less than a particular value. These have a similar flavor. It's just you can rearrange this as counting certain classes in the Floor theory. There's a kind of analog of the eigenvalue size, which is like the action of the class. And then this Calabi invariant is a kind of volume. Also, there's another Weil law which predated this one, which we'll talk about in lecture number 2, where I actually do recover, say, like the volume of a subset of symplectic R4 through similar spectral invariants. Yeah.
So we're getting into the details of this construction. So you want to show you have this infinite Hofer energy.
That's right. I want to show this particular thing has.
Sequence of twists. If you took the smooth ones, isn't their energy blowing up?
That's right.
So what was the? So that wasn't enough, I guess, to say that the.
Well, that is going to be more or less the argument once one has these tools. However, if you didn't have these tools, the basic problem is that in order to have finite Hofer energy, it means that there's in order to have finite Hofer energy, it means there's some way to approximate you without the Hofer distance blowing up. So in other words, if I want to show that this has infinite Hofer distance, I have to show that no matter how I'm approximated in C0, the Hofer distance is not blowing up. So I think what you're saying is there exists a way to approximate the infinite twist such that the Hofer distance is blowing up. But where I need the tools is I have to show that there's no better way to do it. Maybe there's some other way to approximate the infinite twist in C0 such that the distance is.
You could approximate the identity with infinite twists.
Exactly. You could approximate the identity with things where the Hofer norm is blowing up. Exactly. That's a very good observation. Okay. More questions? But I do want to say that the argument that you're sketching is pretty much going to be the argument once we're equipped with these tools. Okay? So also there are some other properties which are helpful. I want the identity to have Hofer norm 0. Also there's a monotonicity property. So if I have two Hamiltonians and one is no more than the other, I want the spectral invariants to satisfy the same comparison. Okay, so here's the two sentences. What are these things? Well, they use the Seiberg-Witten invariance of the mapping torus using some kind of Floor theory. And it's a beautiful story, but we're going to wait until the next lecture to say more about this. But I guess just to say where there is a three-manifold, right? Because to this point, there isn't even a three-manifold. There's just a surface together with a map. I want to just, underline this mapping torus construction. So if I have a diffeomorphism, I can look at its mapping torus. I get a three-manifold. I can do something with the Seiberg-Witten invariance that I'm leaving as a black box. Then I get these PFH spectral invariants. And then from here, we can do the rest of the proof, basically using Laura's argument. So are there further questions? Okay? Okay, so let's do it. So we have to show that this infinite twist is not a finite Hofer energy homeomorphism. So yeah, we're just going to, so the idea is the following. First, we want to show that, so it's going to be an asymptotic argument. In other words, I'm interested in the growth rate of these PFH spectral invariants in D. We want to show that if I have a finite Hofer energy homeomorphism, then the spectral invariants grow no more than linearly in D. And then on the other hand, we want to show that for the infinite twist, the spectral invariants actually diverge with D. Okay, so hopefully you agree that if I show A and B, that will show that the infinite twist is not a finite Hofer energy homomorphism. Okay, so how about A? Well, maybe I'll leave it as an exercise, but A is what you get from this Hofer-Lipschitz property. So remember, the Hofer-Lipschitz property says that I can bound the thing by just D times the Hofer norm. And so if I have finite Hofer distance, that exactly means that I could get this Hofer norm to stay bounded. Okay, so maybe I'll just leave that as an exercise.
Sorry, can you go back to the property?
Sure. Here is this Hofer-Lipschitz property, the third bullet point, and the claim is that you can use this to prove that I get no more than linear growth if I'm a finite Hofer homomorphism. For this, you should use the case where k equals 0. So set k equals 0 to this, then the spectral invariant is going to vanish by the identity axiom, and k is going to vanish because it's 0. And so I just get a bound of the form D times the Hofer norm of H. And since this is a finite Hofer energy homomorphism, that exactly means that I have control over that. Okay. So any more questions about A? Okay. Okay, how about B? Okay, so B is pretty much going to be Laura's argument, that the spectral invariants of the infinite twist have to diverge. So what I do is I approximate the infinite twist with smooth twists. So these are still just twist maps, but they're actually smooth. They're diffeomorphisms of the disk with this comparison. And so maybe I'll just put the whole thing on the board and just run through it. So I apply this monotonicity axiom to show that for each D, the D spectral invariant of the twist is bounded from below by any of these smooth twists. But then on the other hand, I just run the while law for the smooth twists, and I get that the spectral invariants of the twist are bounded from below by the Calabi invariant of the smooth twists. And if I just take the FIs to approximate things better and better, then the Calabi invariant of the smooth twist is going to blow up exactly by that integral condition. And so that says that that the CDs are diverging. CD over D is diverging. So let me just show you a picture, and I can go back in the slide too. So here's my infinite twist. I'm approximating it by smooth twists. The Calabi invariant of the smooth twists is going off to infinity. And so if you just mess around with the monotonicity, you'll find that that means that the CD over Ds are diverging. Okay. And that's that. That's the proof. So, so are there any questions about the proof? Yeah.
Yeah, I thought that the monotonicity only worked for comparing two diffeomorphisms.
That's true, but remember that the definition of the CDs is that it's the C0 limit of the diffeomorphisms. So, if you want a particular CD, then you can approximate it in any way that you want with the smooth ones, and those are C0 converging, and they satisfy this property. So, yeah, that's right. Yeah. Well, no, we're just bounding. So you could compute CD of t if you wanted, but we're just bounding the growth rate from below. But you could, I guess, compute it if that's what you wanted to do. Yeah. Okay, so yeah, so I mean, just to go back then, this is a fully rigorous proof other than the PFH spectral invariants and their axioms. But actually, beyond just time reasons and the fact that I was told to make the first lecture accessible, there is another reason why it's good to think this way, which is that there are other spectral invariants which satisfy these properties. So it just says you need anything you can do with these 5 properties. So, so for example, maybe you hate floor theory. Bad thing to do, but not all of us are perfect. after the proof, Ettmeyer has constructed spectral invariants that he calls elementary PFH spectral invariants that satisfy the same properties, but they're defined only in terms of pseudo-holomorphic curves. And you know, I mean, it's conceivable that there are even more elementary spectral invariants that satisfy these properties, and all you need is anything satisfying these 5 axioms, and you can just run our argument. Okay, so we finished the proof, and then in the remaining 5 minutes, oh, well, sorry, I had some takeaways. Okay, so remember, I'm actually supposed to tell you about low-dimensional symplectic dynamics, and I just told you about an example. But I want you to take away some lessons from this example. So it says that symplectic Weil laws are very powerful. Hopefully I've illustrated that. Also, the spectral invariants and their continuity is a powerful feature. And also, to actually get these invariants, one way to do it is to use Seiberg-Witten theory or Floor theory or something like that. So those are maybe the 3 lessons to take away from the example. And then in the remaining 5 minutes, I wanted to state a more current example. I think Lisa was saying, you know, this is current developments in math, so we should do things current. I mean, the other thing is not current. We did it in like 2020, but I guess there's been like a whole pandemic since then or something. So maybe it's not current enough for your taste. So let's do an even more current example. So I'm not going to do the whole example, obviously, but I'm just going to tell you what it is, and then I think we'll stop. And this will be a kind of a different kind of example, too. I mean, so the previous example illustrated something about surfaces. Now I want to tell you something about 3 manifolds of a more kind of classical dynamical nature. So, okay. I do have until 3:25, is that right? Okay, good. I started to get a little scared. So, okay, so let's imagine that I have a Hamiltonian that's now independent of time, and we're doing low dimensions, so I want my Hamiltonian to be on R4. So there's a conservation of energy principle. I'm still interested in these Hamiltonian flows, so if they don't depend on time, I can apply this conservation of energy, and they preserve level sets of the Hamiltonian, which I'm calling these energy levels. Okay? And so I'd like to understand the dynamics on the energy level. A very classical question is I'd like to understand, you know, how many periodic orbits there are. How many periodic orbits are there on an energy level? So let's just say that a particular energy level, so I'm saying this is it's an energy level because I'm saying the Hamiltonian is equal to C. So say it has a periodic orbit if the flow has a periodic orbit on that energy level. You can ask, okay, so, you know, what happens for a general energy level? What do I actually expect to occur? Well, maybe a first key point is that you could have no periodic orbits at all. So this is a theorem due to Ginzburg and Gorel. It's hardest in this R4 case. It's actually easier if you want to go to higher dimensions. I mean, if you're familiar with the Seifert conjecture, some people call this like the Hamiltonian Seifert conjecture because the Seifert conjecture is about producing vector fields with no periodic orbits. But on the other hand, there's a kind of fundamental result of Viterbo, which says that if the thing is star-shaped, meaning it's transverse to the radial vector field, and let's say closed and smooth, then there is a periodic orbit. So in general, you don't get periodic orbits, but if it's star-shaped, you do. And so then one could ask, okay, so if it is star-shaped, how many do you have? And, well, there was a conjecture about this that I really liked when I was a graduate student, which says that in the star-shaped case, you have either 2 or infinitely many. So a pretty precise prediction. The reason it's not hard to come up with examples with 2. And so the other thing I want to tell you about is, we proved this last year. And so I guess I'll just close by saying, why maybe this is actually a little surprising. So Hofer, Wysocki, and Zender, they did this in the generic case. But you might think, actually, that if you are really interested in these things, that the generic case is maybe different from the general case. Like, say I wanted to know about the number of critical points of a function on the torus. If I'm interested in the generic case, like a Morse function has to have at least 4 critical points on the 2 torus. But you know, there are functions on the 2 torus with just 3 critical points. And so this was a question that interested me when I was a graduate student, like how to go from the generic version that HWZ proved to this unconditional statement. And that's also something I want to talk about in the second lecture. So the second lecture will fill in some details about the PFH spectral invariants, while also explaining how to do this, because the stories have some common ground. So that's the sort of plan. Okay, so I'll stop there. I do see a question here, but maybe there's a desire for questions from the back.
So your first end result is about C0 and C infinity. So C0 contrasts with C infinity. So have people looked at maybe Lipschitz or some kind of other continuums?
Right. Yeah, I think Fatih himself has some kind of works on this kind of thing, but I don't claim to have a kind of encyclopedic knowledge of what's known.
Okay, thanks again.
Okay.
We have done part 2. We just don't have a conjecture.
No, actually, no, it was always planned to be by chalk. Yeah, so maybe I should have said part 2 is by chalk. Sorry.
All the way in the back. You might want to rethink this. I'll give you a minute.
Right, sorry, I should have announced. Part 2 is by chalk because it's kind of more technical. So I thought it would be nice to do it by chalk. Maybe a bad decision, but. Right, exactly. Yeah, so if you didn't like it, move to the back. I don't know. I will say I watched a number of CDM talks, and many seem to do part 1 by slides and part 2 by chalk. Right.
All right, you're live.
Okay, great. All right, so thanks again. So at the end of last time, we were talking about this 2 or infinity kind of result for level sets of Hamiltonian flows. And I was saying I wanted to start to explain the proof a bit. And I said you really need this star-shaped condition. So let me, so we're going to do that. But let me now change language a little bit and help you understand this star-shaped condition a little bit better. So remember, I was saying that the hypersurface of the Hamiltonian flow, it's going to be a 3-manifold. And the star-shaped condition is going to have a significance for contact geometry. And so we want to review some contact geometry. So I'm going to start in a somewhat different setup and then connect to the Hamiltonian setup quite quickly. So say I have a closed-oriented 3-manifold. A contact form on it is just a 1 form satisfying these conditions. And a contact form has a canonical vector field, this so-called Rabe vector field, defined by these conditions. So the Rabe vector field is in the kernel of d lambda. So this condition forces that d lambda has a 1-dimensional kernel. And then I normalize it to have lambda length 1. And I'm going to be interested in also the kernel of this 1 form. It's a 2-plane field. It's non-integrable, it turns out, called the contact structure. And remember, we're interested in the periodic orbits, so I'm going to call those Rabe orbits. So the Rabe orbits are the periodic orbits of R. Periodic orbits. Those have a name. Okay. So maybe we should give an example. So let's say I take the standard 1 form on R4. So then if y is star-shaped, then this implies that lambda restricts to y as a contact form. And what does this have to do with Hamiltonian dynamics? So if, sorry, let me, maybe are there buttons that I'm supposed to use to do this? Well, like this. I see. Okay. I see. Okay. Thank you. Great. Okay, so it implies that this thing is star-shaped. And if y is one of these energy levels, then that implies then the Rabe vector field is proportional to the Hamiltonian vector field restricted to y for some f, some positive function f. Sorry, I'm going to juggle the boards again for a second. I just got a little confused with the electronics here. Okay. Okay. So let me just, to put this in some context then, we were interested in star-shaped hypersurfaces of Hamiltonian flows. And I'm saying those are actually contact. And the contact form is just this one form. This is just the kind of standard primitive of the standard symplectic form, if you've seen it. And the Rabe vector field just agrees with the Hamiltonian vector field. Sorry, this ended up in a sort of strange place in the hecticness of the technology. But are there any questions about that? Okay. So the star-shaped case falls into this Hamiltonian case. And yeah.
So is f like a defining function for the star-shaped domain?
What is this function f?
Yeah.
Well, it just depends on your Hamiltonian. You could have two different Hamiltonians that have the exact same energy level, and they're going to have the exact same Rabe vector field with this thing. And so it just depends on the function.
I think it depends on the inner product of the normal to this hypersurface with the radial vector field. It's fairly
Okay. Okay. So I see what I want. So the theorem that I wanted to state now, yeah, I know, but how do I get out from the? Slide it down so it's not in the shadow, right on it, and then shift it to the top. Because when it's to the top, unfortunately, I can't reach it. That's the sort of problem. But okay, great. So the theorem, this is joint with Mike Hutchings, Umberto Arenovich, and Wei Liu, is that so in fact I always have two or infinitely many Rabe orbits whenever the Chern class of this contact structure is torsion. Okay, so okay, so right. So in particular, this implies HWZ's conjecture. Okay, but it's actually significantly stronger than that. So why does this imply HWZ's conjecture? Well, remember, that's the star-shaped case. In HWZ's conjecture, the 3-manifold is just going to be the 3-sphere. And so this cohomological condition is automatically going to be satisfied. This is just a condition on the Chern class of the contact structure. So it's significantly more general than HWZ's conjecture. Are there any questions about how this fits in? Okay. I want to make several remarks, which maybe for time reasons I won't write on the board. So first, just to situate this in terms of Hamiltonian flows. So to sum up, in the star-shaped case, the flow is Rabe for a particular contact form. Now you might ask what happens not in the star-shaped case. Well, then it's not going to be Rabe, but there still is very interesting structure. So I wanted to use this as an opportunity to direct you to Rohil Prasad, who's in the audience. He's an expert on exactly what happens not in the star-shaped case, and maybe he has many interesting things to say. Also, Fish and Hofer have fundamental work not in the star-shaped case again, but you can't use these contact techniques, at least straight out of the box. Okay. Some other remarks that I won't write on the board is that earlier, Mike Hutchings and I and Dan Parmilano proved this in the case where the contact form is non-degenerate. We'll actually return to that in the proof. I also want to say that the case of 2 orbits, we actually understand a lot. So, for example, in the case with 2 orbits, you learn that the manifold has to be a lens space. You learn that the orbits are linked. You learn a lot of stuff. You learn that the contact structure has to be tight. So we understand the case with 2 a lot. There's a lot of rigidity in the case of 2 orbits. Okay, so hopefully, yeah.
The theorem also applies to, I guess, Finsler 2 spheres, GD6 on those.
That's right, yeah. So this also has implications for Finsler geometry, which was of interest to people. There are generalizations of Riemannian metrics called Finsler metrics, and they have geodesic flows, just like in the Riemannian case. And it's a kind of project, I don't know, at least going back to Anosov, to try to understand which theorems in the Riemannian case continue to hold in the Finsler case. And a very interesting thing that does not hold in the Riemannian case is this 2 or infinity dichotomy for the 2-sphere. I mean, I guess it holds, but the reason it holds is because in the Riemannian case you have infinitely many closed geodesics on the 2-sphere. But in the Finsler case, there are actually examples with 2. So you don't really see this 2 or infinity dichotomy in the Finsler case. And the Finsler people had been interested in whether this theorem holds for a long time. But that won't be the focus of my talk. Okay. So are there more questions? Okay. So in the second lecture, I want to explain this, and along the way, say a little bit about how these PFH spectral invariants are defined. Okay, so first I want to say what the general strategy is. So the strategy is to find what's called a global surface of section for the flow. So we'll find an annular global surface of section R. So I'll draw you a little picture, and then I'll tell you some more about what I want these global surfaces of section to have. Okay, so here's my global surface of section, S. The point is I want to be able to define a Poincare return map. Okay, so here's some picture of what you should sort of have in mind. Okay. So I want S to be a subset of Y. So S is some annulus. S. I want it, say, the interior to be embedded. And I want the boundary of S to consist of Rabe orbits. And the main point is this Poincare return map. So I want that there exists a return map P from the interior of S to itself. So the key point is that the Rabe orbits other than S, so other than boundary of S, should be in bijection with the periodic points of this map P. Okay, so are there any questions with what I mean by a global surface of section? I guess I've been a little bit impressionistic about the definition. Yeah.
Just to get started, do you know that there are at least two? Because you're trying to prove two or infinity.
That's right. Yeah. So you do know that there are at least two. Yeah. For example, I previously showed a while ago with Mike Hutchings that there are at least two. Yeah.
It requires proof.
That's right. It requires some proof. Yeah. But I mean, if you knew that there was a global surface of section, then you would know that there. If you knew that there was an annular global surface of section, then you would know that there are at least two. Right. And the proof will kind of produce an annular.
Oh, so it gives another.
It does give another. Yeah.
There's an intuitive way of thinking
Why there should be a global surface of section?
or why there should be two.
Oh, why there should be two?
There are like some simple explanations.
Well, that's an interesting question. Well, I mean, the way we originally proved that there were two was with this so-called Weil law. So there's a different Weil law in this case, and much like the classical Weil law, it has a growth rate. And it turns out that the growth rate is like the square root of, it grows, it grows like the square root of the parameter. I guess it really grows like the parameter squared if you want to do it in connection with the classical Weil law. Anyways, there's a growth rate, and it's a square. And maybe from that, you need to have two orbits in order to have that growth rate. If you had one, you just couldn't get that kind of growth rate. So, okay, so you have some return map like this. And so if you had this thing, then we could apply this theorem of Frank's. So theorem star would follow from work of Frank's from the 90s. I think if you look at the accompanying notes, I give you the exact reference. What's the theorem of Frank's? Theorem says that if I have an area-preserving homeomorphism of an annulus, and it has at least one periodic point, then it has infinitely many. I guess I should say that this particular return map would have to be area-preserving, because you can show that it's going to preserve the restriction of d lambda to this thing. So maybe I'll write that on the board, because it's a rather important point. So there, it preserves d lambda. Well, I can no longer reach there, so maybe I'll just take my word for it. Okay. So are there any questions about the strategy? I guess I want to also put this in a little bit of context. So yeah, like I said, when I was a graduate student, I was actually interested in this question and maybe even trying to do it with this approach. But part of the difficulty of the approach is that I just have a general contact form here, and I don't have that much to work with. You should compare this maybe with the difference with the example that I ended with last time, where I have just a general function as opposed to a Morse function. So if I had like a Morse function, you have kind of Morse homology, all these kind of things. Here I have just some contact form and not necessarily very much structure to work with that I have to exploit. So to put this in some perspective, for example, it's definitely not the case that every RAID flow has an annular global surface of section, because there are even topological restrictions to the existence of a global surface of section. So in order to produce this thing, I have to find some thing that I can grab onto if I have only finitely many orbits. Okay, so are there any questions about that? So the Franks thing, it says that if I have an area-preserving homeomorphism of an open annulus, and it has at least one periodic point, then it has infinitely many. And so I'm saying if I have this global surface of section, it has this well-defined return map. If I have more than 2 orbits, then that means that it has to have a periodic point, and then I have to have infinitely many. Okay. So how do I find this global surface of section? The strategy looks like this. So I'm going to approximate lambda by non-degenerate lambda n. I won't define non-degenerate, but think of non-degenerate as like Morse. It's analogous to Morse. Okay. So, that's why I was saying that it doesn't look like there's a lot to hang on to, because in the Morse case, there's a lot I can do at least. So I approximate it with Morse functions. Now I want to find a global surface of section for each of the lambda n's. I want to show that I can somehow take a limit. So show that the global surface of section, GSS is just my abbreviation for lambda n, converge to a GSS for lambda. Okay? And I'll see if you have questions, but I first want to say a little bit more about B and C. Okay, so, so far I've still kept things rather accessible. You imagine I have a global surface of section for each of these contact forms, and I want to show that in the limit I get some global surface of section. Seems like quite a hard problem. And so what really helps with this is Gromov's theory of pseudo-holomorphic curves. And I want to explain a little bit about how this works. So, in more detail, so we'll find pseudo-holomorphic curves Cn in R cross Y such that pi of Cn is a global surface of section. Okay? Pi is this map just the standard projection from R cross Y to Y. And we'll use compactness theory. Use compactness for such curves. Okay, so I'll stop to see if you have any questions, and then I'll just give you a quick overview of what I mean by a pseudo-holomorphic curve. So if there are no questions, I mean, maybe I should. Oh, there is a question. Yeah.
Is there annuli in the boundaries of periodics?
That's right. Yeah. So the pseudo-holomorphic curves, that's a great question. Thanks, Dan. The pseudo-holomorphic curves are going to be cylinders, right? So these CNs had better be cylinders in R cross Y, and I have this projection from R cross Y to Y, and I just want the cylinders to each project to annuli that are going to be global surfaces of section. And then the hope is that if I can do a reasonable limit of these CNs, then I can also get the global surfaces of section to converge to a global surface of section for lambda. Okay. Any further questions? Okay, so maybe I should just give a quick crash course on pseudo-holomorphic curves, but I really mean quick. So I mean a kind of primer here. So a J-holomorphic curve primer. So the founding figure here is Gromov. So if I have a symplectic manifold, say I have a symplectic manifold with a compatible almost complex structure. So it's good to study. So Gromov's idea is that it's good to study. I want to study maps U from a Riemann surface into X, satisfying where this is a Riemann surface. Okay? So in our case, so you might be saying, where's the symplectic manifold? I mean, we had a contact manifold, but the nice thing is this R cross Y has a natural symplectic structure. It's just d of e to the s times the contact form. And we're pretty much interested in the case where sigma is a punctured Riemann surface. So that's really all I'm going to say. But Dan was asking about cylinders, so in that case, sigma would just be like CP1 minus 2 punctures. Okay. And before moving to the next part of the talk, I just want to make one more remark and see if you have any questions. So this is the strategy, pretty much what we do. You might ask, why am I demanding annular global surfaces of section? I mean, why not just some global surface of section with genus, whatever? That would actually work for our purposes, but we just don't know how to produce such a thing. It turns out that the fact that Cn is a cylinder, together with some kind of Seiberg-Witten type magic, is actually going to really help this whole thing work. So we'll return to that in a bit. But it's really in the analysis that it's helpful that this is a cylinder and not anything about the dynamics. I mean, Frank's theorem does require that you have an annulus, but there are other things you could do if you got something that wasn't an annulus. It was still a global surface of section.
So when you said part B that you're finding it already for this non-degenerate one, would that solve the conjecture in the generic case? You said already it was known in a generic case.
That's right.
Does it give another
That's right. And in fact, I was also saying that, so HWZ, they have a particular kind of genericity. Already with Dan Pomerlano, we solved it in the non-degenerate case, and we found a global surface of section in that case. Right. Right, but actually, it wasn't necessarily an annulus. It's pretty hard to get an annulus. That's probably the hardest part of the proof, is to get an annulus. But there is a very important point about what you said that is one of the big challenges here. So the problem is, okay, so in general, you wouldn't expect that there's always a global surface of section. So what you want to do is you want to say, assume that there are finitely many orbits, and then find a global surface of section. So you assume that lambda has finitely many orbits, but then the problem is that these lambda n's might not have finitely many orbits. That's, maybe the biggest challenge of the whole thing. So I guess the strategy says, okay, so it suffices to assume that lambda has finitely many orbits. Now you approximate it by lambda n's. You actually can't assume that the lambda n's have finitely many orbits, but anyways, you'll show that those have global surfaces of section. But anyways, that gets to your question, though, because you were saying, does this prove it in the non-degenerate case? Well, no, it would only prove it, well, in a way it does prove it in the non-degenerate case, but it actually proves something stronger, because these are not going to have finitely many orbits. They're going to have some kind of strange structure that comes from just being close to a degenerate contact form with finitely many orbits, which is a rather subtle thing. So it is true that the arguments that we do certainly suffice in the non-degenerate case, but you should think that these forms actually have some kind of somewhat subtle structure. They're close to a degenerate form with finitely many orbits, which is a bit of a strange structure. Okay, so more questions?
Do you think every three-dimensional wave flow has a global surface of section?
That's a great question. I do think that every three-dimensional Rabe flow has a global surface of section, and I think it's a good question to think about. However, it will not in general be an annulus, because as I said, there are topological restrictions to having an annular global surface of section.
There's some counterexamples.
There's even counter. Well, yeah. I mean, maybe you have your own opinion on whether it's true, but that would actually be the cleanest way to prove this two or infinity thing, is just prove every Rabe flow has a global surface of section. That would also do it. Okay. So anyways, okay, so how are we going to find these global surfaces of section? Well, that's where this ECH PFH stuff is going to come. So this is now where we link up with the previous lecture. And this is why it's important that the lambdas are non-degenerate. So okay, so we're going to use what's called embedded contact homology. So I'm going to write this as ECH. And it's a cousin of the PFH from the previous lecture. Okay, so I want to explain then not just how, all right. So let me explain how this works with the okay. So this ECH, it's going to be the homology of a chain complex ECC y lambda n. Okay, so this chain complex, let me tell you what it is. This ECC is generated by certain sets of Rabe orbits the chain complex differential delta counts J-holomorphic curves. Okay. So the best way to illustrate this is with a picture. So here's Y. Okay, and I want the curves should be asymptotic to Rabe orbit sets as the R parameter goes to plus or minus infinity. So if I give the R coordinate S, we'll say as S goes to infinity. Okay, so maybe I'll put this a little bit higher for you. So this is a curve counted by the chain complex differential. Anyways, if you're not an expert, the point is just that we're getting some J-holomorphic curves. I'm a bit vague about exactly what they do, but anyways, you get some J-holomorphic curves, but importantly, they're definitely not necessarily annuli. Now, they're actually also not quite suitable for finding global surfaces of section, but there's a related structure called the UMAP, which is going to be suitable for this. I want to say a little bit about how this works. And then I want to compare a little bit with periodic floor homology. And tell you a little bit more about the proof. And I guess I should say that this counts certain curves. So as I say, I'm being a little vague about exactly which Rabe orbit sets I want to consider. And especially it's the curves you should be looking at. I'm being a little bit vague about exactly which curves to count. But we'll go back to that in a minute. Okay, so the really important point where the Seiberg-Witten theory comes in is that you rig this in such a way that it recovers the Seiberg-Witten floor theory of the manifold. So this is due to Taubes from 08. And it's very powerful because it allows you to translate known results about Seiberg-Witten into results about ECH. So for example, it implies that, that ECH always has infinite rank. Okay, so maybe we should stop for a minute and appreciate that. I mean, remember, the game here is we're basically trying to find infinitely many Rabe orbits. And this thing is the homology of some chain complex generated by some Rabe orbits. So you might think that we're done, actually. but you know, the point is that if I have an orbit and I go around it many times, I still get an orbit. So I don't necessarily get infinitely many orbits like this. In fact, there are examples with just 2 orbits. But I get a lot of juice to work with this isomorphism. And importantly for our purposes, what's very important for our purposes is that there's a map on ECH called the U map. So on ECH, which counts certain curves of index 2 of what's called Fredholm index 2 through a marked point. Let's just say through some point in R cross Y. So just to add to this picture, okay, so I'm now going to take the curve counted by the differential and I'm going to instead look at the curves counted by U. If you're not a specialist, I mean, you know, don't really worry about, well, anything really. but you know, maybe if you're not a specialist, the most important thing is really this index 2 thing that I said. Because I think we should stop for a moment and then try to explain what we're doing. Okay, remember, we wanted some suitable curves for finding a global surface of section. And what we're saying is that you get these UMAP curves. I mean, I have to say for a second why they actually exist, but it's going to come from this isomorphism. You get these UMAP curves, and I'm saying they actually live in a 2-dimensional moduli space. So the picture that you want is that ideally, and I will write this on the board, ideally, I hope that if I take one of these curves and I move in the component of the moduli space containing it, that I foliate all of this four manifold, R cross Y. That's the significance of this number 2 here. Then you hope that that forces the curve to project to a global surface of section. Okay, so let me write that on the board. We'll switch this, and then we'll start to kind of wind down with some concluding remarks here. So the kind of hope is there's a UMAP curve even remember a cylinder such that its deformations foliate R cross Y, and then the hope is that this should imply that the thing converges. So optimistically, and that this should imply that pi of this curve, let's call it Cn, is a global surface of section. So let me give this thing a name. Okay. So like I said, I want to start winding down and kind of emphasizing what I think are the most important points. I did start 2 minutes late, so I'm going to take 8 minutes. So maybe the most important point is I want to compare where we are with this picture to what we want and to try to explain this picture. Okay, so the first point is, remember I wanted a cylinder. This is definitely not a cylinder. The reason that I'm emphasizing this is that that's, in a way, the hardest part of the proof, is that you get these curves, but they're not necessarily cylinders. We'll talk in a minute about how you get any curves at all. Okay, so we wanted a cylinder. We didn't quite get a cylinder. We have to talk about that. The other thing that I want to say is just this index 2 condition, especially if you're not a specialist. So I wanted this thing to project to a global surface of section. That seems like a very hard thing to guarantee. But I'm saying optimistically, I might hope that if this thing actually lives in a two-dimensional family of curves foliating the entire manifold, then I can somehow leverage that to show that it projects to a global surface of section. So are there questions about that kind of picture? Yeah.
Yeah, if you project a whole foliation, you get like a foliation of Y or something.
Yeah, you get what's called an open book of Y. Exactly, yeah. So the different curves are going to project to like kind of pages in what's an open book structure of Y. That's right. Okay. So like I said, I want to sort of try to wind things down a little bit with some concluding remarks. Okay. First, I want to say how you actually get these UMAP curves. So we know that there are some UMAP curves by this isomorphism. Some such curves by this isomorphism star. Let me actually label the isomorphism star if I'm going to quote it. In other words, okay, so there's this UMAP on embedded contact homology. There's a similar UMAP on Seiberg-Witten Floor cohomology. And I was saying that this Floor cohomology is known to be quite non-trivial. In particular, it actually has a non-trivial UMAP. Actually, importantly in the proof, every power of the UMAP is even non-trivial. So the juice from this isomorphism is going to come from the fact that it's like a factory, which is going to give us a lot of curves, but it doesn't guarantee us that the curves are, it doesn't give any guarantee that the curves are cylinders. Okay. So, okay. So one thing I want to say in my concluding remarks are what this has to do with the first lecture. So, So remember in the first lecture I had these periodic floor homology spectral invariants. There's a cousin, so PFH from the first lecture is very similar. It's essentially the case where Y is the mapping torus. There's maybe some disclaimers to use some language from Samet's talk. But so if you like this description of ECH, you get a similar description of PFH. So the PFH spectral invariants come from filtration on this floor complex called the action filtration. And that's going to be beyond the scope of what we can say. And OK, so that's just a remark with how this fits into the previous lecture. In the remaining 4 minutes, I just want to say then a few words about how we overcome the challenges. Or at least what I really want to do is list the challenges for you. So to recap, we need to resolve the following challenges. So to recap, to resolve, I would say 3 big challenges. So one, so how to get UMAP cylinders. Two, so even if we have the cylinders, do they actually give a global surface of section? And 3, How do we actually get something meaningful in the limit? Okay, and well, obviously I don't have time to tell you how to do this, but I will at least say a few words. I guess I want to say that, I did try to write this out in some detail in the accompanying lecture notes. Also, another thing I want to say is that this is actually quite hard. Like, I would say that these three things are, probably this paper is like the most challenging paper I've written. None of these things are especially easy things to do. So let me just say a few words. Okay, so for getting the cylinders, you need new ideas to control the topology of ECH curves. I think these ideas I'm quite excited about. They're useful for other results. For example, I have a recent paper with Rohill in the audience constructing compact invariant sets. And the ideas here are one ingredient there. So for the first thing, we need new ideas for controlling the topology of ECH curves. This second thing is a very beautiful story. I mean, say I actually had a cylinder. Well, basically, you want to show that it foliates all of R cross Y. If it lives in a two-dimensional moduli space, you're in some decent position, but there's a big problem with compactness. You could imagine that I have as I move in my moduli space, you could imagine that I have some kind of breaking occurring or something. And so you need to do a kind of detailed analysis. But luckily, there's a very standard compactness theory here called SFT compactness. So I would say that actually part 2 is pretty standard. It's really part 1 and part 3 that are interesting. The answer to part 3 involves some technical analysis about the ends of these curves. So it turns out that standard theory says that these curves, Cn, they're going to converge. Not only are they going to converge to Rabe orbits, but they're going to converge exponentially fast. That's just standard theory. But what you can show is that using some kind of ECH magic, the rate at which they're converging does not go to 0. So this is one of the more interesting points in the proof. I'll just wave my hands at it. But you can imagine these Cn's, they're converging at some exponential rate to each Rabe orbit. They're converging, say, with rate lambda n. And I need to show that the lambda n's are not going to 0. And it turns out by some magic that they're not. And that means that in the limit, I do get some kind of meaningful exponential convergence to Rabe orbits. And it turns out that once you have that, the kind of standard techniques that people do work very well. But maybe like 10 years ago when I thought about the problem, I would say it's kind of 1 and 3 that I was really missing. So I think I'll pretty much stop there. One final thing I wanted to say just about the whole lecture series is, so I think we have a good handle on low dimensions, more or less, by these kind of techniques. In high dimensions, it's a bit different than what Lisa was saying in her talk. I mean, I know Lisa was saying that in high dimensions, it's a very different story. In high dimensions, we actually just don't know. Like, you could ask, are there n or infinitely many orbits, in dimension n? And we just don't know. I mean, who knows? So it's a big mystery to me what happens in high dimensions, and hopefully some of you will help clear it up. Okay, so I think I'll stop there. Sure, yeah, definitely. So especially, I mean, you're a man of algebra. It's not so complicated. I mean, it's actually a filtered Floer complex. Maybe I'll just say it over here. So it's maybe a little bit easier to say in the ECH case, just because it's slightly easier to describe the filtration. So maybe I'll just do the ECH case if that's okay. But it's all basically the same. So if I have a Rabe orbit gamma, I can define its action to be the integral of my contact form over gamma. And this extends linearly to sets of orbits. to the action of a set of orbits, where theta is a set of orbits. And so it actually gives a filtration on your floor complex. So it implies that I can study ECH upper L, which is going to be the homology of the subcomplex generated by orbit sets with action less than or equal to L. Okay, so for every real number, I get this subcomplex, and it has a map. There's a map from ECHL into the full ECH. So then if I have a class in ECH, I just look at the first value of L in which it's actually in the image of this map. So if you wanted to do this concretely, it can actually be made very concrete. If you want to do it concretely, it's just a minimax. Namely, this thing is the homology of some chain complex. So generators here are sets of orbits. So if I take a particular class, given a representative, I look at the maximum action of all the particular orbit sets in the representative, and then I find the best representative with respect to that maximum action. So it's a minimax, and that's the spectral invariant. And you can pretty much do the same thing with PFH. Those are the PFH spectral invariants. So then you remember I actually indexed them by D. So that means I just have to find some particular classes in the PFH. But actually, there are some choices. We don't really do it in a canonical way, but you can find some reasonable classes in the periodic floor homology of the two-sphere is a quite explicit thing, and you can find some nice classes. So yeah, so it's actually not a very hard thing, really.
It's a pretty naive question. I mean, it looks like topologically you always get the same picture. Like you have a topological free sphere, and then it's got this open book decomposition by cylinders. I mean, is there any way to argue by continuity, like you sort of have one for the standard sphere? And
Right, yeah, some people sort of think about these kind of things. Yeah, I mean, I think Hofer and his collaborators have been thinking about these kind of things for a long time. Yeah. In the case where there's two orbits, you get exactly that. In the case where there's two orbits, remember I said it's a lens space. I mean, you actually get a foliation by projections of cylinders. So, but yeah, some kind of continuity for global surface for open book decompositions is kind of, thinking there. But I mean, yeah, we definitely do not know how to prove that there even is a global surface of section, even in the S3 case, with no conditions at all. So, so what I'm saying is it's an interesting idea, but it's hard to work in practice. Sure.
So, I mean, usually, what you said about exponential convergence rate, right? So usually, generically, the exponential convergence rate is some sort of smallest positive eigenvalue.
That's right.
Some self-adjoint operator.
Exactly.
As you go to degenerate limit, that eigenvalue always goes to
No.
goes to 0, right?
No, that's the magic. That's the magic. 0 becomes an eigenvalue as you go to the limit, but that doesn't mean that the eigenvalues for these particular curves have to converge to 0. So basically, it's like if you work it out, it's determined by the mod 1 rotation number of the ends of the cylinder. And basically, the mod 1 rotation number has to go to 0, but there's two ways the mod 1 rotation number could go to 0. It could go to 0 or it could go to 1 or something, And it makes a big difference which way it goes. And in the ECH case, by the so-called partition conditions, it just turns out that it has to go to 1, which means that the exponential convergence. And this was kind of the main thing that I missed when I thought about it 10 years ago. Yeah, so that's like a really essential point. And I consider it kind of magic that it works out.
All right, let's take that again.
Okay.